Start chapter 5. Of course, integrals. I don't like to put the name up there or the title up there, just that, because it's a lot of preparation before we get to see what they are and how we calculate anything. So it's a lot of preparation. So let's talk about summation notation, also called sigma notation. So we have, as I said, we have a lot of preps before I even write 5.1. So there are a few things that we need to talk about. So this is not even 5.1. We have it's all over in chapter 5, but we need to discuss what this means. Okay, so let's suppose we want to add numbers 1, 2, 3 dots till 20. I'm not going to list all of them. I am going to use a notation to condense all this very nicely. So for the first index, the first number is 1. For the second index, I have 2. For the third index, I have 4. And you can say, what are you talking about index? In a moment, I'll explain. So this is the symbol for sum, but it's a Greek symbol for sum, and it's called sigma. Why we don't use this symbol instead of that? It's because we have to write something under and we have to write something above, and this is not really convenient, a convenient notation, but it's the same thing. It means the sum. So how many numbers I have? Well, from I equals 1, from the first number till the 20th number. Of what? Of I. Okay, so what does this mean? When I is 1, I have 1. The sum says plus. When I moves on to 2, then I have to add 2. When I is 3, I move to 3, dot, dot, dot. When I is finally 20, I get 20, because that's what I have. So I is the index. It's the location of any term. The first location, the second location, what do I have? I have on the second location, I have 2. What do I have on the 20th spot? I have 20. Normally the indices we like are I, J, or K. You can use any, it doesn't matter. But these are the indices that are most common. 1 represents the lower limit. Has nothing to do with the notation limit, nothing. It just says, where do I start? What is the starting point? It's called, by chance, there is no connection to this, it's called the lower limit. Of course, this will be called the upper limit. And this is the generic term. So here's an example. If I have, let's say, the sum from j equals 2 to 5, just an example, of 3j plus 2. What does this mean? It happens that this summation notation, the index starts at 2. It doesn't start at 1. Fine. So when I plug in 2, I get 3 times 2 plus 2, plus. I move on to the next one, which will be 3. So the summation says plus 3 times 3 plus 2, plus. When j is 4, 3 times 4 plus 2, plus finally I get to the upper limit, and I have 3 times 5 plus 2. Now, how will I determine this calculation with these sophisticated ones? Not all of them have this. So here's how we start. Go to Math and scroll up to Summation 0. Again, not all calculators have this option. Go up to 0. And you see, if you see at the bottom, it gives us the index. Well, in the calculator we have X. We normally prefer I, J, and K, but the calculator doesn't have that. So it's X. It starts at 2. Jump up to the upper limit of 5. And this is strange, but the calculator, some calculators require these parentheses not to be these parentheses. So I have to use another set of parentheses. So I have 3x plus 2, close the parenthesis. And when I press enter, maybe we should do this first by hand, because I just chose a simple example that can be easily done by hand. So let's see what we get. So this is 6 plus 2, 8, plus 9 plus 2, 11, plus 12 plus 2, 14, plus 15 plus 2, 17. So this is 22, and this is 28. So I have 50. So when I press enter, I should get 50. So there are some properties. Of course, every time we invent, we didn't, the Greeks did, but every invention follows with some properties, of course. So here are the properties. Generic terms can be written as A sub n, B sub n, and so on and so forth. So here's the first property. There are 3 properties. These 2 can be combined in one, and I should. And here's the third one. So the sum of A sub n plus B sub n from n equals 1 to whatever, 100, just as a number. Then this is the sum from n equals 1 to 100 of A sub n plus the sum from n equals 1 to 100 from B sub n. Of course, if this is a sum, I can separate, I can calculate this and I can calculate that and then add them up. It's the same property we have with the limit. The limit of f of x plus g of x is the limit of f of x plus the limit of g of x. The same kind of property. Of course, the second property is with minus, identical. The limit of f of x minus the limit minus f minus g of x is the limit of f of x minus the limit of g of x. Same idea. And of course, the last one is with a constant. So the sum from n equals 1 to any number you want, a constant times a sub n. Of course, the constant goes in front like with everything else. So these are the properties that we will be using for the summation notation. Now, before we start anything in chapter 5, there are 4 identities. I don't like to tell you this, but every now and once in a while I had to. There are 4 identities that need to be, and I don't like that, memorized. If we understand something, we don't have to memorize it. It will always stay with us. This is very easy to prove, but however, we need to memorize the answers of 4 identities. Again, I don't like that, but every once in a while we need that. Okay, here's the first one. The sum from I equals 1 through n from 1, just digit 1. Here's the second one. From I equals 1 through n from I. Here's this, that's the second one. Here is the third one. And here's the last one. Okay. So first of all, what does this mean? On the first spot, I have 1 plus. That's what the summation notation says. Plus 1 plus. A third spot, 1 plus. Dot, dot, dot. Exactly 3. Plus. What is the last one? N. For when the spot is n, I add 1. I'm jumping. Okay. So what is the answer? What do you think the answer will equal to? I wrote it ahead of myself. Of course it's n. So it's 1 plus 1 plus 1 plus 1 n times, it must be n. Okay, what does this mean? We just discussed that. It's 1 plus 2 plus 3 plus dot 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 plus n. And now here's the formula. n plus 1 divided by 2. Yes, this we have to memorize. Sorry. Okay, what will the third one mean? Well, the same thing. When I is 1, when I is 2, when I is 3, dot, 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 3 dots, plus when I is n squared. This is the most difficult to remember, is n plus 1, 2n plus 1 divided by 6. And yes, it needs to be memorized. And here's the last one, which is easy. Easier than that. Well, what does this mean? Of course, the same thing. 1 to the third plus 2 to the third plus 3 to the third plus dot, dot, dot plus n to the third. And what does this equal to? Well, it happens to be exactly the same, but squared. n plus 1 divided by 2. So this says really nothing. You understand how that works. This one, these two are identical except that a power 3 has power 2. And this one is sort of similar, just it has an extra factor and not 2 in the denominator but 6. And you're going to say, what are we doing with this? And I'm going to say in a minute, or maybe in about an hour, or maybe Monday. Because I still need a lot to explain before we get to apply this. But for now, we need to understand what they mean. Now you can say, prove any of this, and I will have to use mathematical induction if you ask me to do that. Induction. To prove any of these to you. If you say, I don't believe you, then I'll have to use mathematical induction on any of these to show you how it works. And we will be able to prove any of this. Now, for example, as a nice example, if you would like to add numbers from I equals 1 to 1,000 of I, 1,000 of I would be 1 plus 2 plus 3 plus dot, 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 plus 1,000. So 1 plus 2 plus 3 plus dot, 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 plus 1,000. Well, it will take you a while to add these. It's not going to be easy. But it's very easy because n is 1,000. 1,000 times 1,001 divided by 2. So I'll divide by 2 is 500. So the answer is 500500. So 500,500 is the sum of the first 1,000 numbers, natural numbers. And using this formula, you can do whatever else you want, from any number starting with 1 to whatever. If you start at 10, then you have to subtract the first 9. Okay, so this is simplifying our life because, first of all, we don't really want to write this. We prefer to write that. And now we have a way of determining or calculating those. So, first of all, we know the summation notation. We learned 3 properties of the summation notation, and we learned 3 identities that we have to memorize. Okay, so now 5.1. 5.1 should be, and it's not, it says the title is areas and distances. Well, I'm going to change the title. I'm going to write it in parentheses, areas and distances. But I don't like that. It's basically the Riemann sum. This is what we are really talking about in this section. So let's take a very simple function. Let's say f of x equals x squared plus 1. Let me stop and ask you if you have any questions for me. Any questions? Anyone? Can you follow? Anyone?
I'm doing good so far.
Okay. So let's take a look at this function. If I graph it, I'm only interested in the interval 0, 2. I don't want to graph the function everywhere. I know how to graph this, right? It's x squared up 1. Right? X squared and then up 1. But I'm not interested to graph the whole thing. I'm interested to graph it only between 0 and 2. So 1, 2. 1, 2, 3, 4. So when x is 0, y is 1. When x is 2, 4 plus 1 is 5. So somewhere up here. This is the interval 0 to 2. Okay, so here's our question. Find the area under f of x between 0 and 2. I'm asked to find this area. Okay, so I have 3 methods that we are going to look at. In all these situations, we are going to divide the interval into several equal pieces. So let's suppose it doesn't say, or it is mentioned, it doesn't matter, but I want to start slowly with n equals 2 subintervals. First method, using the leftmost point. The second method, using the rightmost point. And the third method, using the midpoint. So we are looking at 3 situations. Leftmost point, rightmost point, and the midpoint. What what's all this? Okay, in a minute I'll explain. Okay. I'm going to graph the interval 0 to 2. Here is my graph. And here's 1. And I was told use 2 subintervals of equal length. Okay. So I'm using the first method, the area with the leftmost point, 2 subintervals. Then we're going to look at the area rightmost point with 2 subintervals. And then finally the area with the midpoint with 2 subintervals. Leftmost point, I split the area into 2 rectangles using the height the leftmost point. So the area with the leftmost point then, left 2, is the base of this rectangle, which is 1, multiplied by the height of this rectangle, which is f of 0, plus the base of the second rectangle, which is 1, times the height of the second rectangle, which is f of 1. F of 0 for our function, f of 0 is 1, times 1 is 1. F of 1 will be 1 plus 1, which is 2. So the area is 3. Question: is this area an overestimation of the actual area or an underestimation of the actual area? I left a lot, right? So this is definitely underestimate. Let's see what happens with the rightmost point. Same interval, same function, 1, 0, and 2. Now I'm estimating using the rightmost point. So this rectangle has this height now. This rectangle has the rightmost point height now. So therefore the area with right 2 is still 1 for the base times f of 1, plus still 1 for the base, but times f of 2. Again, our function is x squared plus 1. F of 1 is 2. F of 2 is 4 plus 1 is 5. So 1 times 5 is 5. So the area is 5. When I use the rightmost point for this function, what kind of area do I get? Do I get an underestimate or an overestimate of the correct area, of the actual area? Over.